Today's notes are going to go over Vsepr theory. Vsepr stands for valence shell electron pair repulsion theory. This theory is applied to molecular, also known as covalent compounds. Those are compounds that are covalently bonded, so a nonmetal to a nonmetal, and this helps us predict their 3D shape. Now, I want to mention before we go further that ionic compounds do not use Vsepr theory. And they form what is known as a crystal lattice. So that's why most ionic compounds are known as salts. They do form these sort of like crystallized structures, all very similar patterns, positive, negative, positive, negative. So ionic compounds don't follow this valence shell electron pair repulsion theory. They have their own shape, again, a crystal lattice. So for molecular compounds, we use Vsepr in order to predict what our 3D shape will look like. Now, the idea is that when atoms are covalently bonded together, the valence electrons around the central atom, both the bonding pair of electrons and the non-bonding pairs of electrons, want to position themselves as far away from each other as possible, because basically all electrons, whether or not they're bonded or unbonded, they're negatively charged. So negatively charged particles repel other negatively charged particles, and so that forces them to be as far away from each other as possible. So based off of the number of bonding pairs of electrons and non-bonding pairs of electrons, we can start to determine the shape of our molecules. Now for us, we're only going to be learning about 5 shapes. There are more shapes than this, but we're going to keep it pretty simple. So we're going to be learning about linear, trigonal planar, tetrahedral, trigonal pyramidal, and bent. So just to go over a few abbreviations that you're going to see here, we're going to be using Ca in our notes to represent the central atom. BPE is bonding pairs of electrons. MBP, if you see me write that, is our non-bonding pairs of electrons, and our ligands are our branches that are coming off of our central atom. So really we are concerned about how many branches are coming off our central atom. That's one of the most important parts. So let's get started and talk about our shapes. So let's start with linear. So the first thing you'll notice in your notes is the idea that all 2 atom molecules are always linear. So that might be something like I2 or CO. Those would be good examples. HF. Those are all 2 atom molecules. They're always going to be bonded just to each other. So they're always going to form a linear molecule. So I bonded to I, H bonded to F. These are always going to form linear molecules. Now, our shapes get more complicated when we start to add potentially more atoms to our molecule. So we're going to do a 3-atom molecule looking at BeCl2. Now beryllium is a double exception for us. So beryllium is an exception, and we talked about it in your covalent notes because it is a metal that makes covalent bonds. And it is also an exception because it only needs to get to 4 valence electrons. All right, so beryllium has 2 valence electrons already. Each chlorine is bringing 7 valence electrons. And so I get to use in my picture 16 valence electrons. So the first thing I'm going to do is draw my Lewis dot diagram. So my Lewis dot diagram gives me information about where my central atom is and how many branches are coming off my central atom. So beryllium is going to make 2 bonds because it needs 2 more valence electrons. Chlorine is already at 7, so it only needs 1 valence electron, so it's only going to make 1 bond. So I'm going to put beryllium in the middle. And then it's going to be bonded to chlorine on either side. And then I'm going to finish off their valence shell by adding in the extra dots. So my Lewis dot diagram should look something like this. Each chlorine has 8 valence electrons, and beryllium is happy with just its 4 because, again, it's an exception to our octet rule. Now, when I have a central atom, my central atom being beryllium, when my central atom has 2 branches, so remember our ligands are our branches, you can write branches down. If I'm looking at this beryllium, I've got 1 branch coming off on the right, and I've got 1 branch coming off on the left. So that's a total of 2 branches. And on this Lewis dot diagram, if I'm looking again at my central atom, I'm looking for non-bonding pairs of electrons. I see that there are no non-bonding pairs of electrons. When you have 2 branches and no non-bonding pairs of electrons, you will form a shape that is known as linear, like the shape above, but this time with 3 atoms involved. So our linear shapes are really easy to draw. They're going to look just like the Lewis dot diagram because these branches are as far away from each other as possible. So these electrons here and here, the ones that are in those bonds on those central atoms, these are the electrons that want to be as far away from each other as possible. So these electrons could not be any further away from these electrons, and these electrons, again, couldn't be any further away. And these electrons are currently about 180 degrees apart. So when we make a linear shape, my bond angle is going to be 180 degrees. All right, so we're going to do this for each of our shapes. So we're going to go on to our next shape, and we're going to talk about trigonal planar. And boron, again, is an exception that was in your notes. So boron is an exception because it only needs 6 valence electrons to be satisfied. Now, boron brings 3 because it's in family 13. Each fluorine is going to bring 7 valence electrons. So in my picture, I get a total of, 14 plus, that's 24 valence electrons. So you get 24 dots in your picture. So if I were going to draw this, I'm going to put boron in the middle because boron is going to make the most number of bonds. It wants to make 3 bonds because it has 3 valence electrons and it needs 3 more. So boron will go in the middle. It'll be surrounded by my fluorine. And then I'm going to add on the additional valence electrons. Now again, boron is an exception, so it's happy with its 6. So then I'm going to finish drawing my picture by adding the remaining valence electrons onto fluorine. And if I were to count up all my valence electrons, it should add up to 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Great. Everybody's happy. So now let's take a look at how many branches I have. So again, I'm looking at my central atom, and I see on my central atom that I have 1, 2, 3 branches coming off of it. And on my central atom, again, I'm going to look for non-bonding pairs of electrons. Well, all of these are in bonds, and there are no non-bonding pairs of electrons, so there are none. When there are 3 branches coming off the central atom and no non-bonding pairs of electrons, we form a shape known as trigonal planar. That means that everything is on the same plane, and we'll get a chance to build these atoms during class. But if I were going to draw these, I want to draw it so that each of my bonding pair of electrons are as far away from each other as possible. So if I'm drawing this bonding pair of electrons, it's trying to be far away from these ones, but also far away from these ones. And again, a circle is 360 degrees. So when I draw this, I'm going to be drawing my 3 branches so that they are approximately 120 degrees from one another. So each of these branches are about 120 degrees away. And this one too, and also this one. All right, so let's do our next shape. So we already did one like this in the notes. Carbon goes in the middle. It becomes surrounded by hydrogen. Carbon brought 4. Each hydrogen brought 1 valence electron. So I get a total of 8 valence electrons in my picture. Everybody's happy. Remember, hydrogen is exception because it only wants 2 valence electrons. Carbon has its 8. So when I'm looking at this picture, I see my central atom, which is carbon, has 4 branches coming off of it. So it has 4 branches. Again, all of the electrons coming off of carbon are in a bond. So there are no non-bonding pairs of electrons. When this happens, you form a shape called a tetrahedral. So this is a better 3D drawing than I can draw. So it's going to look sort of like this. And again, we'll build them in class. But when we draw this, and we're trying to draw in 3 dimensions, because this is a 3-dimensional molecule, in order to draw it, we put carbon in the middle, and then we're going to have one of our hydrogens going straight up. And then one of our hydrogens is going to be coming out to the side. And then one of our hydrogens needs to look like it's coming out at you. And in order to draw that, we draw a triangle that looks kind of like that. And we add a hydrogen to it, so that's going to be this one that's coming out at you. And then we need to draw a hydrogen that looks like it's moving away from you. So in order to draw that hydrogen, we normally draw sort of dashed lines that sort of make a little triangle shape, and we add a hydrogen there, and that is our 3-dimensional version of this picture here. And again, we'll build these in class so that you can see them. Now, these down here make like a little pyramid, and this one sticks straight up. And all of these are as far apart from each other as possible, and they're all sort of evenly distributed around a 3D sphere. And so all of these branches, because it's not actually all on the same plane and it's 3-dimensional, these all end up being about 109 degrees away from each other. Again, because we're thinking about that in sort of a 3-dimensional shape, in a sphere. All right, so that's your tetrahedral. Let's move on to your last 2 shapes. We've got trigonal, pyramidal, and bent. So I'm going to draw the Lewis dot diagram for NH3. Remember, hydrogen is our exception. It only needs 2 valence electrons. So nitrogen has 5. Each hydrogen brings 1. So you get a total of 8 valence electrons in this picture. Nitrogen will go in the middle. Hydrogens will surround it. And then nitrogen, again, is not an exception. It wants 8 valence electrons. I've only drawn 6 valence electrons. So the last 2 will go up here. So this is your Lewis dot diagram for NH3. We've drawn similar ones to this in our notes. If I'm looking at nitrogen, nitrogen is our central atom. I can see that if I'm looking at branches coming off of it, that I have 1, 2, 3 things, 3 branches coming off of it. So this has 3 branches. Now again, if I'm looking at that central atom, I can see that there are these electrons that are not participating in a bond. Those are non-bonding pairs of electrons. I have 1 non-bonding pair of electrons. When this happens, I form a shape that is called trigonal pyramidal. This looks a lot like the tetrahedral. So if I stuck a little branch up there, it would look just like a tetrahedral. But there is no branch there. Instead, what I have are 2 non-bonding pairs of electrons up there. So when I draw this 3-dimensionally, I'm going to start with my nitrogen. And then one of my hydrogens will be coming out to the left. One of them is going to look like it's coming out towards you in a little sort of tripod. And then one of them is going to look like it's moving away from you. And then, of course, I want to draw my non-bonding pairs of electrons. So that is what the 3D drawing, the Vsepr drawing for NH3 would be. Now, in our tetrahedral, these were 109 degrees apart. But what ends up happening, and if you look back at our notes, you'll see that non-bonding pairs of electrons repel more than bonding pairs of electrons. And this becomes really important because if these electrons on here had been a regular branch, then these all repel equally. But these actually repel more. So these are going to push these branches even closer together. And because they're getting pushed slightly closer together, instead of being 109 degrees apart, they end up being about 107 degrees apart. So they end up being a little bit closer to one another. And again, that's because the non-bonding pairs of electrons repel more than our bonding pairs of electrons. So it's going to push those branches even closer together. All right. So we're going to move on to our last shape, which is going to be bent. So I'm going to draw my Lewis dot diagram first because our Lewis dot diagram tells us, again, how many branches we have and how many non-bonding pairs of electrons. So hydrogen, each one brings 1 valence electron, and oxygen brings 6. So we have 8 valence electrons in this picture. Oxygen will go in the middle because it wants 2 more electrons, so it's going to make 2 bonds. And hydrogen's only going to make 1 bond. So I put oxygen in the middle, and then I'm going to put hydrogens around it. And the hydrogens are now satisfied, but the oxygen isn't. Plus, I get 8 dots in my picture, so I get to finish oxygen's octet by adding on the additional valence electrons to it. Now, for oxygen, I can see that it's my central atom, and on my central atom, I have 2 branches coming off of it. So 2 branches. And in this case, I have, if I'm looking at my picture, 1 non-bonding pair of electrons, and I have a second non-bonding pair of electrons. So I have 2 non-bonding pairs of electrons. This shape would also happen if I have just 1 non-bonding pair of electrons. So if I have any number of non-bonding pairs of electrons in my central atom, I will make this bent shape. So a bent shape looks like this. And when we draw it, because none of them are coming out towards you or away from you, we can sort of just draw everything on the same plane. So I'm going to draw oxygen in the middle. I'm going to draw the hydrogens or the branches down here. And the reason that they are down here is because the non-bonding pairs of electrons are pushing them really hard or harder in that direction. Now, the reason that I drew it like this, and this is going to make a lot more sense once we build it, is that this is sort of like a tetrahedral shape, believe it or not. And so if I were drawing this as a tetrahedral, there would be a hydrogen coming out at you, right? And then there would be a hydrogen coming up here. But instead, these are non-bonding pairs of electrons, and it's in a 3-dimensional space. So instead, since I can't really draw this non-bonding pair of electrons 3-dimensionally, we draw them both at the top so that you can see in the picture that they're going to be pushing down on these other branches. Now, again, because we were based off of that tetrahedral shape, and what we've really done is replace branches with non-bonding pairs of electrons, we're not going to be 109 degrees apart. And because we actually have additional non-bonding pairs of electrons, we're not even going to be 107 degrees apart. Because these non-bonding pairs of electrons, because I have 2 of them in this particular picture, right, they're going to push even harder on these branches, and it causes the branches to get pushed to about 104.5 degrees apart. So 104.5 degrees is the bond angle between those branches. Now, what we're going to be doing next class is we're going to be building these molecules so we can see how these Vsepr shapes that we just drew here, again, these are our Vsepr shapes, how they sort of depict what happens in the 3D molecule. So we'll build them next class with our model kits. And that's it for your Vsepr notes.